Hi, everyone. It's an absolute pleasure to be here. Thank you for having me. Today, I'd like to give you maybe something a bit different than what you've seen before. I'd like to actually get into the nuts and bolts of what deep learning looks like. Artificial intelligence and machine learning, they have rapidly become integral parts of our lives. You encounter them daily, often without even realizing it. Have you ever wondered how your smartphone predicts the next word you're about to type? Or how Netflix knows exactly what the next show you might want to watch is? Maybe some of you have even used Siri and Alexa or an equivalent kind of thing to ask for directions, and they've flawlessly guided you to where you needed to get to. All of these technologies are powered by AI and machine learning. So today we're going to dive a little bit deeper into how machines actually learn and the methods they use. And by the end of this talk, I hope you'll have a solid and hopefully intuitive understanding of AI's foundations, particularly the exciting role played by neural networks like the multi-layer perceptron. So let's get started. How do machines learn? Machine learning has become an essential tool for solving complex real-world problems that traditional methods struggle to address. So let's consider a few examples. Take the stock market. Predicting future stock prices is notoriously difficult. And of course, it would be difficult because if it weren't, we'd all be making enormous sums of money, but we aren't. And the reason is because there are an enormous number of variables that interact in very complex ways. Now let's go to an example from sports. Selecting the best athletes for a team or predicting an athlete's performance is again incredibly difficult because there are lots of variables that interact in complex ways. Now, take for a second the challenge of classifying objects from an image or from video. Picture in your mind a person sitting on their couch with a cat sitting in their lap. Could you even imagine writing a software program to detect the boundary of the cat, to detect the boundary of the person, to somehow disentangle the two as being separate objects, and then to ignore the couch and ignore the rest of the room? It's a mind-bogglingly difficult challenge. And then what about generating realistic conversation like ChatGPT does so well? How would you even begin to do that from a software perspective? Now, these are all things that machine learning and AI excel at. Why? Because what we're talking about today, machine learning and AI, is a systematic approach to finding patterns in high-dimensional data through learning. Now, if we want to get specific for a moment, machine learning tackles a variety of problems, each requiring a unique approach. So let's explore some of the primary types of machine learning, of the machine learning tasks. First, we have binary classification, a simple yet very powerful and important technique. Binary classification involves categorizing data into two distinct groups. So let me give you a super simple example that is immensely important to industry. And in fact, a technique like this that I'm about to describe might even underpin billions of dollars of transactions. Now, imagine you have a factory and the factory needs to process millions of tomatoes from a number of farmers. Now, these tomatoes are streaming through on a conveyor belt. And now what you want to do is sort the tomatoes into ripe and unripe. Maybe the ripe ones are red and the unripe ones are green. And if you can detect an unripe tomato, you can use a blast of air to blow the unripe tomato off the conveyor belt. This is binary classification. It's a simple but very, very important task. And there are many applications of binary classification apart from just tomato sorting. Next, we have clustering. Clustering is a powerful machine learning technique, and I've indicated clustering in the diagram on the top right here. It's a powerful machine learning technique that you use particularly when you're working with unstructured or unlabeled data. So imagine for a second that you find in your drawer at home a hard drive, and on that hard drive, there are thousands and thousands of photos that you've taken on your mobile phone. Now, some of these photos, and none of them have names, so that's completely unlabeled. Now, some of the photos are pictures of you. Some of the photos are pictures of you and your friends. Some of the photos are pictures of you with your family. And some of the photos might just be photos of cars or cats that you've seen on the road. Clustering is an approach that would help you to, in a systematic way, to group the photos by similarity. And it helps you to discover structure in the data that you didn't know was there. It's a really important technique that will then help you with further analysis, labeling, or decision-making. Next, we have regression tasks. That's this bottom left image here of the straight line graph. Now, regression tasks we're going to talk about a lot in this presentation. Regression is the art of fitting a model to input data that will allow you to make predictions about new data. A common example is predicting house prices. So the regression algorithm might examine a number of different factors. So let's say you're trying to figure out how much a house should cost. Maybe you would look at the location of the house, the size of the house, and the number of bedrooms. Now, a regression task would try and find a function that finds a relationship between those three variables and then gives you a price. Once your model has been trained properly, you can then feed in new data about different houses, and it should give you a good estimate of the house price. Now, in this image on the slide, the data are these blue dots. The green line is the function that we are fitting to the data. Now, many of you will have come across straight line graphs before, y equals mx plus c, or in slightly different notation I've written here, the function of x is equal to w0, a weight, plus w1, another weight, multiplied by the input. We are going to be talking about weights a lot in this presentation. And you can think of the coefficients on your straight line graph as weights. And if you're trying to find the best straight line to fit through a data set, you're finding the best weights for that straight line. Now, finally, I've illustrated with a picture of a man pulling his hair out here. We have dimensionality reduction. This sounds super complicated, but actually what it is a method to make things simpler. Imagine trying to choose the best starting team out of a group of football players. The key things to look at, clearly, are things like their fitness, how many goals they've scored recently, their past performances, and their cohesiveness as a group. But would you look at variables like their favorite TV shows? Does it matter that player B has an aunt and two uncles? Does it matter that player D has a cat? Of course not. Dimensionality reduction is a technique to remove variables that don't matter so that we can focus on the things that do. Each of these machine learning techniques addresses different problems effectively. However, the real power lies in knowing when and how to apply each approach. So, in all the examples I've just given you on the last slide, if we really think about what we're doing, the essence is to take something, which we'll call an input, and transform it into something else. We'll call it an output. So in the example of the house, we take an input, which is the house's location, size, and number of bedrooms, and we transform that into a price. Or we take your photos as an input, and we transform them into a group of photos that all have similarities. Or we take tomatoes as an input, and we transform them into two sets, a set of ripe tomatoes and a set of unripe tomatoes. Now, this thing in the middle that does the transformation is super important. We call it a function or an unknown function. And the essence of machine learning is to figure out what that function is. Now, to make this slightly more relevant to you, let's go back to the example of a straight line graph. At the bottom of the slide, I've reminded you that a straight line graph is a function. It takes the input x, and then the way the function manipulates that input is it multiplies the input by a weight, in this case m, and then it adds what we might call a bias or a weight. They're roughly the same, but you add another thing to it, and you create y, which is your output. So this is what we're trying to do in machine learning. We're trying to find weights that define functions that best approximate the learning space that we're trying to generalize. So let's shift gears now and get into the specifics. Formula One, like all sports, is about competition and high performance. The difference between winning and losing could be 1/100th of a second. So let's think for a second about how we can help a Formula One team choose the best possible car for a given race. Now, these races take place all over the world. Some of them are in locations that are extremely hot. Some of these races take place at high altitude where there's literally less oxygen in the air for the engines. Some of the locations are often wet and rainy. We need to help the Formula One team take all of these factors into account and more. So let's consider factors like track surface, weather conditions, tire choice, aerodynamic settings, fuel efficiency. And let's try and construct a model that will predict the average lap speed of the car with those inputs. So our goal is to create a model that takes in, say, for example, the driver. Now, we can label the drivers 1, 2, and 3. It takes in the altitude of the track. It takes in the expected weather on the day. We could call hot and sunny 1. We could call cool and dry 2. We could call rainy 3. It takes in the chosen tires. And then it outputs a predicted average car speed at that track. Now, how can we do this? One answer, because there's always many ways to skin a cat, but one answer is to use regression. Let's quickly go back to our example from slide 3, predicting the house price. In that image, we were trying to fit a straight line to noisy data. And that straight line was y equals mx plus c. We were trying to find the weights that made that line best approximate the data. Now, in this example, which is a much more complex example, because we have many, many more factors that may interact in ways that we don't understand. So we're trying to fit some unknown function, but to what data exactly? Well, data is very important, and you can believe it, the Formula One team will almost certainly have about 20 years worth of racing data that we can use. So we can train our model using that data. So imagine for the last 20 years, we know exactly what car the Formula One team put into the race, and we have the lap time of the car for every lap in the race. And so we'll know the average car speed. So we've got our inputs, but we also have the output. We know the speed, and we can use that knowledge to update and train the weights in our model so that we can make a model that then can predict car configurations that it's never seen before. Now, if we tune the model over thousands and thousands and thousands of races, it will start to learn the patterns in the data. And this is what we're trying to do. Because if we can create this model that can then predict the average car speed for configurations it's never seen before, then our Formula One team can try out many, many, many different kinds of configurations and just simply pick the best one that is right for those conditions. Now we can really get into the details. We're going to talk about something called the multi-layer perceptron. It sounds very complicated, but don't worry. It is possibly one of the most fascinating examples of deep learning that is accessible. And it is the workhorse of machine learning regression. The multi-layer perceptron is a powerful and versatile type of artificial neural network that has significantly advanced the capabilities of machine learning. Imagine the neural network as a simplified model of the human brain, comprising interconnected neurons. Now, these neurons I've shown as these dots in the bottom right-hand side. We've got the green dots, the purple dots, and the red dots. The neurons are organized into layers, and the information is fed forward through the network layer by layer. These layers, the way the model is architected also is that you have an input layer which receives the input data. So those green dots are where we input the known information. So we're going to input their driver, altitude, weather, and tire selection, say, for example. Now, then we have the hidden layer, and then finally the output, the hidden layers, and then finally the output layer. So let's talk about what the hidden layer sees. Now, I have labeled one of those neurons as 1 in the image. So this purple neuron in hidden layer 1, what does it see in terms of those inputs? Well, when you initialize a neural network, you'll just initialize all the weights as being effectively some random uniform distribution. Now, one of the things that we can do is we can look at this neuron number 1 and what it might see. For example, it might see 3 times driver minus 2 times altitude plus 10 times weather minus 1 times tires. That's maybe what it might see. Those numbers that I gave you, 3, minus 2, 10, and minus 1, those are the weights that connect that neuron to the input layer. Now, if we go to the neuron below it, it is also connected to the input layer. So it will also have those 4 weights. So the first hidden layer is connected to the input layer with 5 times 4 equals 20 weights. Now we need to find these weights somehow. But if you look, there's also a second hidden layer. Now that second hidden layer is connected to the first hidden layer. Each one of those neurons is connected to the 5 behind it. So there are 5 times 5, which is 25 weights. And the same is true for the third and the fourth hidden layers. All in all, if we add up all the weights, there are 100 weights that we need to find. And there are also another 21 things called biases, which are basically like weights. So in total, we have 121 things that we have to fit and find to make the model fit the data. Now, just think for a second how much more complicated this is than the simple straight line graph. In the simple straight line graph, you had y equals mx plus c. You've got 2 weights. That's it. We've now got 121 parameters. So you can imagine how complex this function can be and how complex and rich some of the patterns are that it'll be able to find in the data. Now, before I start talking about how we actually find these weights, let's just talk a little bit about where the magic happens in the multi-layer perceptron. The magic happens in the hidden layers. So those neurons that I've labeled in purple. Now, something that we've got to talk about now is, I spoke about, that neuron number 1, maybe it sees 10 times driver minus 2 times altitude plus blah, 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 blah. But what does it output? Well, the way that neurons work is they need to be really activated before they will output anything. So what the neuron has is a thing called an activation function. Now, this function is designed to be very similar to how the neurons in our brains actually work. And I want to describe the way the activation function works, kind of like this. Imagine you're wearing your headphones and you're listening to music, and your friend comes to try and speak to you. You know, if they just come and talk to you quietly, you'll ignore them and you'll do nothing. If they come and kind of, elbow you a little bit, and you might just go, come on, go away. You'll be kind of at an intermediate state of agitation. But if your friend comes and really shakes you and starts shouting at you, you'll take your headphones off and go, what? That is kind of similar to how the activation function works. The activation function will do almost nothing if you don't give it a strong enough input. And that's the way our sensory neurons in our brain work. If you activate it a lot, it will fire. And this is a non-linear function, and it's very important. It can't be a linear function. It's a non-linear function, which is absolutely crucial. And we're going to get onto that in a slide or two from now. But its non-linearity is what allows the network to learn complex, intricate relationships within the data, far beyond what you'd be able to learn with simple linear patterns. In fact, the non-linearity will allow us to essentially model something as complex as the human brain. But let's now go back to talking about how we find these weights. Now, in the diagram here, I've explained basically how you find the weights. We're not going to go into the exact mechanics of it, but we can talk about it in the questions afterwards. Essentially, let's go back to the Formula One example. We've got 20 years worth of data from our Formula One team. Let's randomly select half of the data. And what we're going to do is we're going to feed into the model known car configurations, and it's going to output an incorrect answer. It will be wrong. And luckily, we know how fast the car was for that configuration because the Formula One team kept track of all this data very well. So based on how wrong the model is, we then go make an update to the weights. And there's a special mathematical procedure to update these weights based on how wrong the model is. And then you feed in some more data into the input, and it's still wrong. So you make an adjustment. And you feed data in, it's wrong, you make an adjustment. Now, over time, the model will get slightly less wrong, because as you've been tuning these weights, it's starting to explore the complex landscape of this function that we're trying to find. And it's getting better and better at predicting the underlying training data. Now, over enough training cycles, eventually it is predicting numbers that are very, very close to being correct. And so the error between what it's predicting and what it should be gets very small. And now our updates to our weights are only little, only very small. So at some point, we're going to stop and we're going to say the model is trained. And it might be a good idea to then test the model on a validation data set, maybe the other half of the data set, to check how well it's generalized to data it's never seen before. But if you've done everything correctly and the model has been updated appropriately, you've now got a powerful tool to put in the hands of the Formula One team. Because if the model has generalized correctly, you can put in any car configuration you can think of. You can write a computer program to basically iterate over every conceivable car configuration and literally just pick the best configuration for the highest speed. So what I'd like to do now quickly, though, is just address the key areas of maths that you're going to need to pay attention to if this is something that speaks to you as a professional calling. The first area is called linear algebra. And, personally, for me, linear algebra is, easily one of the crown jewels produced by the human mind. It stems from an incredibly simple question. If I have two straight lines, do they intersect? Or are they parallel? What about if I have three planes in three-dimensional space? Do the planes intersect in a single point? Do they intersect in a line? Do they intersect everywhere? Are they the same plane? Are they parallel? Do they intersect nowhere? Now, these incredibly simple questions lead us to systems of equations, which you've probably done when you're finding the intersection of two straight lines. But systems of equations then go on to become matrices. Matrices then become fascinating properties of matrices, like spectral properties and so on. Matrices then become tensors, and tensors are essentially higher dimensional matrices. And this is a beautiful and powerful subject in mathematics. And if you get all the way to matrices and tensors and you don't want to do machine learning, you can do general relativity, quantum mechanics, you can do anything else you want to do because it's used everywhere. So pay attention to it and make sure you have a strong foundation. Now, the second area is calculus, more specifically matrix and tensor calculus. So we spoke about matrices in the just previously. Now in terms of linear algebra, you can do calculus in linear algebra too. So matrix and tensor calculus is very important because I didn't talk earlier about how we update the weights in the model. And this is where calculus comes in. To find the weights of our model, it basically involves taking the derivative of the weights in the model with respect to the error in the prediction. And this is the beauty of it, because that is essentially what you do. And then you're able to back propagate a correction to the weights. So back propagation is the technical name for how we update the weights in our model systematically. And I don't think it's a stretch to say that back propagation probably underpins what is becoming a multi-trillion-dollar industry. So moral of the story is pay attention in calculus and learn to love it. This, I think, is incredibly important result. It's the universal approximation theorem. And it's got really powerful implications, to be honest. So in the example we spoke about, namely the multi-layer perceptron, the conditions are if it has a nonlinear activation function. Now remember what I said about the activation function. If you don't input enough strongly into it, it won't do anything. And then it's got a transition region, and then suddenly it fires and it's outputting as strong as it can. If your model has a nonlinear activation function, like the one I showed you, and if it has at least one hidden layer, then that model will satisfy the universal approximation theorem. And what this means is that that model will be able to represent any continuous function to arbitrary precision, just as long as we have enough weights in the model. Now, this is incredibly meaningful because what it means and what we are starting to see already out there in industry is that we might one day be able to create a numerical model of the human brain and create machines that truly think like we do. So let's discuss this point together. Thanks, everyone.